begin now properly. Now, as you can see, this talk is on symmetry. The title is Can You Tell Left from Right? That's the title. The subtitle is What Symmetry Tells Us About Elementary and Elementary Particle Physics. The repetition of the word elementary in the title, of course, is not a mistake. I meant elementary physics. That's what I'm going to spend most of my time on. And then we will, near the end, talk about what it tells us about elementary particle physics as well. In particular, we will be talking about one symmetry, reflection symmetry, or parity symmetry. I'm going to explain what these terms mean as I go along. But first, let's take a look at what symmetry is defined as. So I just went on Google and took a screenshot of the page that comes up when I type symmetry on the Google search engine. And gives me some definitions. It tells me it's a noun, it has the quality of being made up of exactly similar parts facing each other or around an axis. It also says something else. It says there are other meanings like correct or pleasing proportion of a part of the parts of a thing, similarity or exact correspondence between different things, and so on. So there is a technical meaning to the word symmetry. There are also non-technical meanings. Now, if you move away from Google and go into something slightly more technical, let's say Wikipedia. I've just copied this from Wikipedia. These are the first few lines of the symmetry section, symmetry page on Wikipedia. It starts with this, symmetry. This comes from a Greek word, which means agreement in dimensions, due proportion, arrangement. And in everyday language refers to a sense of harmonious and beautiful proportion and balance. This is very important. Symmetry makes, in things, leads us to a sense of beauty. But it also goes on to say in mathematics, symmetry has a more precise definition and is usually used to refer to an object that is invariant under some transformations. So we will spend quite some time in this part, the mathematics definition part, or its applications to physical systems. But before we go there, let's do something about this beautiful proportion and balance thing. So let's take a look at a few pictures of symmetric objects. The very first picture is one which, well, if you leave aside the fierce aspect of it, you can see that there's a very pleasing bilateral symmetry in the face of the tiger. Just imagine the straight line drawn right down the middle of the nose. The left and right parts are almost identical. And I'm not sure whether this was the case, but maybe this was the reason why one of the most famous poetic uses of symmetry has involved the tiger. William Blake wrote in his poem, "Tiger, tiger, burning bright in the forests of the night, what immortal hand or eye could frame thy fearful symmetry?" Of course, fearful, that's understandable. This is a tiger after all. Well, the same bilateral symmetry can be seen in a less fearsome object, the butterfly. Here, again, if you just drew a line right down the middle, you would see the left and the right parts almost perfectly match each other. So this is what we mean by bilateral or left-right symmetry. Or you could even think that of a plane which is normal to the page right now, and along this middle line, if you reflected one half of the butterfly in that plane as if the plane were a mirror, the other half would emerge out of that. So if you were to look at the butterfly before and after the reflection, you should not be able to tell the difference. Well, bilateral symmetry is there not only in nature. In fact, if I just kept showing pictures of bilateral symmetry in nature, that might exhaust the entire time I have for this lecture. Since I don't want to do that, let's move to architecture. This, of course, is one of the most exquisite examples of bilateral symmetry that you can come across. And I don't have to tell you which building this is. But this was built, of course, around the early 17th century, 1620s or so. a bit later perhaps. My history is a bit messed up. 1650s to be more precise, I guess. Around 50 years or 100 years before that came these. These are the ceiling carvings from the Dilwara temple in Mount Abu. One of the most beautiful pieces of architecture that I've seen anywhere. And this is another picture of that. You can see the bilateral symmetry also. You can see much more symmetry here. If you rotate the system, this picture, for example, through a particular angle, you should not be able to tell whether the rotation has been carried out. There is a catch there. I'm going to come to that soon. Well, it's not only in India that you see symmetry in art. Is replete with many examples of extremely symmetric and geometrically pleasing designs. And these were all sort of medieval period examples. Coming to more modern times, you have the Baha'i temple, the Lotus temple in Delhi, which again has a lot of symmetry aspects. We could in fact devote a whole lecture to the various symmetries which this particular architectural marvel has. But let's move on to the next example. All these have been from the continent. So the next example I've chosen is from outside our immediate neighborhood. Again, something which should be familiar to many of you, especially those of you who have seen or read this Da Vinci Code by Dan Brown. This, of course, is a glass pyramid, which is in front of the Louvre Museum, which many people consider to be a marvel of modern architectural engineering and so on, and many others consider to be an eyesore, which should not be there. But be it as it may, it's an extremely symmetric building, and you can again see many symmetric aspects of this thing. Well, coming back from pictures of architecture, let's take a look at the human face. I'm pretty sure most of you know who this person is, and the two pictures do look like him. George Clooney, of course, voted the most handsome person on earth several times. But you would all agree, perhaps, that this is not really very aesthetically pleasing. I'm pretty sure you can make out what has been done to make these pictures. The actual picture is this one. This is George Clooney in person. And what has been done here is basically you have taken half of the picture, half of the left-hand side, mirror reversed it, and make the whole picture out of this. That's the left-hand picture here. The right-hand picture here is, of course, take the right side meaning right as I see it. This is really the left-hand side of Clooney's face, and double that up, and you have made this picture. Now, this, of course, aesthetics is a matter of personal taste, but I'm pretty sure most of you will agree that among the three pictures that you have seen here, the left hand and the right one, which are, of course, exactly symmetric because that's how they were prepared, the actual one, which has a degree of asymmetry, which is almost symmetric, but has a degree of asymmetry, is perhaps more pleasing to the eye than these two artificial looking pictures on the two sides. Now, this aspect of symmetry with a bit of asymmetry mixed in is going to be part of the theme of my talk. Well, most people know about this. This is a situation where you have a molecule, say a carbon-based molecule, whereas the central carbon atom is connected to 4 different objects. And such an object has this property that if you mirror reversed it, this one on the left, the mirror reverse is on the right, these two molecules cannot be superposed onto each other by translating and rotating. So these are called stereoisomers or enantiomers, and many physical properties are nearly identical, but sometimes they show drastically different chemical properties, especially in biological systems. One enantiomer may be active, may be a drug, the other one may simply be completely inactive. And there's a good reason for that. The good reason, of course, is most of these, okay, I'm simplifying this a bit, but in most situations, these chemicals work by docking into regions of bigger molecules. And it's very much like a lock and key system. And if you mirror reflected a key, that will no longer fit in the same lock, especially if it were a three-dimensional key. So the levoenantiomer may be may be an active drug. The dextro one may simply not be of any use whatsoever. So this kind of asymmetry is there in biology everywhere. And of course, this kind of asymmetry is there in human life everywhere. I shouldn't have to tell you who these people are, but you also know that left-handed people are a minority compared to right-handed people in the general population. So if you take a person out at random, most likely he will favor his right hand. So this kind of asymmetry is there everywhere. Of course, you can have examples like this one. Somebody who is ambidextrous, or in this case, as a story in the film goes, somebody who taught himself to be ambidextrous, somebody who can use both hands equally, simply to be able to save time and do more. We have plenty of examples of ambidextrous people in our literature and our classics. Dhananjay, Arjun was, of course, ambidextrous. I've forgotten exactly what his name, which particular one of his names meant ambidextrous, but he could use both hands to draw his bow, and that is why he was a much fiercer fighter than many others around him. And this ambidextrity of the universe, which is not so apparent in people, but much more obvious and apparent in the world around us, is going to be part of what I want to really talk about. So now we come to the question that was in the beginning of my title. Given the fact that most people are right-handed, given the fact that right-handed enantiomers behave differently from left-handed ones, and so on, this seems to be a rather easy thing to do. If I could establish connection with an alien civilization, can we teach this alien what we mean by left or right? And given the fact that most people think that left and right are very different, and almost 99.99% of human beings have no difficulty in distinguishing left from right, this seems to be a very, very simple thing to do. But we are still asking the question, can we do this? And before that, why should we even bother doing it? So in order to answer this, let me take a brief detour and talk about one person. I'm not going to take much time talking about this because again, this would have been a full lecture on its own. Frank Drake, in the early 1960s, came up with this idea of Drake's equation, which essentially tried to figure out how many civilizations that we have in our galaxy that we can communicate with, or that we can that are sending us communications which we can detect. The background of this came really from a paper by Giuseppe Coccini and Philip Morrison. This was published around 1959. It was called Search for Interstellar Communication. And these two authors argued that by 1959, by the time that when they were writing this, radio telescopes have become sensitive enough to pick up transmissions broadcast by civilizations orbiting other stars. And they also proposed that if these civilizations had any sense, they would really be sending us radio transmissions around the 21 centimeter wavelength, because that's a standard emission line from neutral hydrogen, and hydrogen being the most abundant material in the universe, any civilization who is advanced enough to know what the universe is made of would definitely make use of this wavelength to communicate. So what Drake did was he booked well, let's talk about his equation first. Drake essentially wrote down this equation as a way of estimating how many such civilizations are there, so that is it at all worth trying to communicate with them. And I'm not going to go into the full length description of this. Anybody interested can look up Drake's equation on the net. It's very well documented. The only point I want to make is there are various factors which go into this equation which you want to multiply. For example, the average rate of star formation per year in our galaxy, then what is the fraction of stars which have planets, and so on. Now some of these factors are pretty well understood, and as science is progressing, we know more and more about these factors. There are other factors which are more speculative. So ultimately, you should not really take the final result which Drake's equation gives as something which is sacrosanct or written in stone, but you should think of this as more as an estimate. Drake had estimated by the data, using the data available to him, that around 500 civilizations should be sending detectable signals to us. Today, if we use our current estimates of various numbers which have been upgraded over time, that number goes to more than 2000. So in principle, we should be able to communicate with alien civilizations. And what Drake did was Drake set up something called the Ozma project. He booked the 25-meter dish, that's the picture of the 25-meter dish here, at the National Radio Astronomy Observatory in Green Bank, USA. And there he started extraterrestrial intelligence of what is today called the SETI, Search for Extraterrestrial Intelligence. And there's one reason why computer enthusiasts, especially Linux enthusiasts like us, are very excited about this, is that the huge amount of computing power needed for SETI is actually powered through parallelization, which today is driven by Linux systems. Of course, back there in 1960, there was no Linux, there wasn't even Unix, and they had much less computing power than today. But despite that, Drake tried very hard, and for 3 months, we made July, 4 months in 1960, he trained this 25-meter dish to 2 particular stars in the neighborhood, Epsilon Eridiani and Tau Ceti, and tried to look for signals. He did not succeed. In fact, the Ozma project did not succeed then. It was repeated around 10 years later, 10 to 15 years later, in a second, more powerful version in the same facility, but using a bigger telescope. But that also, the Ozma 2 also failed. But let me just tell you why it was called Ozma. Some of you may be aware of this. There's a wonderful set of children's tales called The Wizard of Oz. There are around 14 books and written by L. Frank Baum. And in this, Ozma is the name of the princess of this land of Oz. Oz is a land which is in the middle of an inhospitable desert. Nobody can go there. Somehow Dorothy manages to land up there and comes back with news of it, or tales about this wonderful land which nobody believes, of course. And that's what the stories are about. But in this Ozma, in this story about Oz, there was also a character called Long-Eared Hearer, somebody who had huge ears so that he could put his ears on the ground and listen to signals from very far away. Drake, who was a big fan of these Wizard of Oz books, named his project the Ozma project simply because he wanted to talk about this listening to signals coming from very far away. In a sense, his telescope was his long-eared hearer. So this brings us to the problem that was alluded to at the beginning of my title. Assuming that the Ozma project succeeded, could we carry out a meaningful conversation with the aliens? In fact, this question has often been asked: if you could detect an alien signal, what should you do? And T.D. Lee, somebody whose work we are going to talk about later, had answered, just keep quiet. Don't say anything. Don't let them know that we are here. But I'm pretty sure human curiosity will not allow you to do that. So if we got signals from aliens ever, it's almost certain that we would like to talk back. And ultimately, radio communication using binary code should work out. And we can even transmit pictures by zeros and ones. That's pretty easy to do. You can take a picture, imagine that it's some rectangular picture that you want to scan and send. You can break it up into many tiny boxes and just tell the alien using your binary code whether each box is dark or black or white, let's say, by using zeros and ones. That will at least be able to give the alien this picture, and all the alien would have to do is, once he or she gets, or it gets the information, they can actually scan the picture, recreate the picture going from left to right, top to bottom, and so on. The only problem is, can I tell the alien what do we mean by top and bottom, and what's left and what's right? So in order to be able to make sure that this alien can reconsider our picture properly, he should know which way to go. If instead of going from left to right, it went from right to left, would end up flipping the picture over. It went from bottom to top, again another flip, vertical flip in this case. Now top and bottom should be easy. After all, gravity works here, and that alien must be living in some planet which is hospitable, and that planet would have gravity. So the alien would definitely have this idea about what is top, what is bottom, which way is up. There's no problem with that at all. So gravity will simply tell us how to communicate top and bottom to the alien. Well, left and right, on the other hand, turns out to be surprisingly subtle. Apparently, despite all this thing about left and right being very different, left-handed people and right-handed people being differently abled or having different strengths, left-handed enantiomers being different from right-handed ones, and so on, physics apparently does not seem to distinguish between the two at all. That statement comes with a caveat. We are going to come to that soon. That is why I say, or at least did not seem to. So this was a real question. Can I teach an alien what is left and what is right? And the name the Ozma problem was given by Martin Gardner. Many of you know him as the creator of some of the most wonderful mathematical recreational problems ever. He wrote a book called The Ambidextrous Universe, and I don't know whether you can see it, but the subtitle of the book goes Left, Right, and the Fall of Parity. That essentially is what I'm going to talk about in the rest of the lecture. So, because of course, Drake did not really worry about this issue at all, but given Drake had this project called the Ozma project, Martin Gardner came up with this name, the Ozma problem, for this issue about communicating with the alien, in particular communicating what is left and what is right. So the question was, is there a way to communicate the meaning of left by a language transmitted in the form of pulsating signals? I'm directly quoting from his book here. And by the terms of the problem, we may say anything we please to our listeners, ask them to perform any experiment whatsoever, but with one proviso. There is to be no asymmetric object or structure that we and they can observe in common. Now, this is what the statement of the Ozma problem was, as Martin Gardner stated it in his book. But Gardner was not the first person to talk about it. In fact, one of the first people to talk about it in print happens to be the great Richard Feynman. And I can't resist this, although this may be a bit boring to some of you, but I can't resist quoting Feynman in toto from his book. This is from his lectures in physics, volume 1. Imagine that we are talking to a Martian or someone very far away by telephone. We are not allowed to send him any actual samples to inspect. For instance, if we could send light, we could send him right-hand circularly polarized light and say, that is right-hand light, just watch the way it is going. But we cannot give him anything. We can only talk to him. He is far away or in some strange location and he cannot see anything we can see. For instance, we cannot say, look at the Ursa Major. Now see how these stars are arranged. What we mean by right is we can't do that. We are only allowed to telephone him. Now we want to tell him about us. Of course, first we start defining numbers and say tick tick 2, tick 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 3, and so on. So that gradually he can understand a couple of words and so on. After a while, we may become very familiar with this fellow and he says, what do you guys look like? We start to describe ourselves and say, well, we are 6 feet tall. That's Feynman talking about himself, of course. He says, wait a minute, what is 6 feet? Is it possible to tell him what 6 feet is? Certainly. We say, you know about the diameter of the hydrogen atoms? We are 17 billion hydrogen atoms high. That is possible because physical laws are not variant under change of scale, and therefore we can define an absolute length. This is very important. Feynman is stressing the fact that physics is the same for that alien and me. So my hydrogen atom is the same size as his hydrogen atom. So I should be able to tell him exactly how tall I am by using something we have in common. I don't have to send him the hydrogen atom. He has hydrogen atoms, he should be able to detect or measure the diameter than himself. And so we define the size of the body and tell him about the general shape is, and so on. Well, he says, you're certainly very handsome fellows. Now what is on the inside? So we start to describe the various organs on the inside and we come to the heart. And we carefully describe the shape of it and say, now put the heart on the left side. This is where Feynman made a small mistake. After all, he was not a biologist. Strictly speaking, the heart is not really on the left side. It's near the middle, it's tilted to the left side. But anyway, that's what he meant. And here's where the kicker is. He says, meaning the Martian says, the left side. Now problem is to describe to him which side of the heart goes on without his ever seeing anything that we can see. And without our ever sending any sample to him of what we mean by right. No standard right-hand object. Can we do it? And Feynman then of course goes on in the very next section of his lectures to describe how we can do it. But let me give you a slightly different version of how it seems we should be able to do it. We can use elementary electromagnetism. After all, electromagnetism involves laws of physics. They should be the same for everyone, for me as well as the alien. And in electromagnetism, we do have a lot of right hand and left hand rules, right? So it should make a difference whether somebody is using a right hand or a left hand as far as these rules are concerned. So let me just show you one example of this. This is something which every student of physics has seen. A current carrying wire. I am grabbing it with my right hand, of course, only figuratively. It's a very bad idea to grab a live current carrying wire. But if you wrap your fingers around the wire with the thumb pointing along the direction of the current, then your fingers will give you the direction in which the magnetic field is. And so if you look at this from the top, you could simply say, okay, let me put a lot of magnet needles around the wire. This is a top view, so the current is coming straight at me. And now I can see that we have all these needles arranged all around. And it's pretty easy to see that as you go along the needles from the south pole to the north pole, so along these arrows, as you move along, the needles are turning, and they're turning to the left. So isn't this easy? You could just tell your alien in whatever language you have ultimately come up with, take a wire, drive current through it, arrange magnetic needles all the way around it, and go along the magnetic needles from the south pole to the north pole. And as you move, you're going to turn, the needles are going to turn, and they are going to turn to the left. And that's what left means. Of course, the opposite direction is right. So the problem is solved. There's only one catch there. The catch is the north pole. How does the alien decide which one is the north pole? We, of course, have a north pole and a south pole on the Earth. But that's essentially because we have a magnetic field. The Earth has a magnetic field. And Earth's magnetic poles are very close to our geographic poles, geographic north and south poles. And as far as we know, that's not necessarily true, because there could be even today, we don't really understand the mechanism of geomagnetism that well. We have several models, some of which are reasonably accurate, but even today we are not very sure of this, and there are plenty of things which turn around their axis, plenty of cosmic objects which don't have a magnetic field. Or say the sun keeps on turning on its axis in a particular way, so it does have a north pole and a south pole, if you want to call it that, but its magnetic field keeps on flipping around. It's not a constant. But neither is the Earth, by the way. There have been around 200 times since its creation, we know this from geological records, that the Earth's magnetic field has flipped. So what we call South Pole today may very well have been the North Pole. It was the North Pole, say around 80,000 years ago or so. So for our alien, he may even have a North Pole and a South Pole, but that may very well not match with ours. So his north and south may be the opposite way. And if he went around following our prescription, he would actually be turning to the right instead of to the left. So the all-important thing is, you could not use the right-hand rule that we use to tell somebody what is left or what is right, unless I could send this person my magnetic needle, which we are forbidden to do by the rules of the problem. So this is where symmetry comes in. The point is, the laws of physics are invariant under many things. For example, if you rotate your coordinate system, the laws of physics stay the same. They should also stay the same. Okay, the should within quotes. You replace a right-handed coordinate system by a left-handed one, which is what happens when you see your coordinate system in a mirror. The question is, do they really say the same? Because if they did, then the world in the mirror would have been the same, would have behaved exactly the same way as our ordinary world. And if this is true, there would have been no possibility of a solution for the Ozma problem. There would be no way in which you could use just communication, just description of the world around you to tell somebody whether something is left or right. Now, I'm pretty sure most of you who are listening can think of many, many ways of doing this, but I will urge you to think about it at your leisure, and you will find that as long as the laws of physics did not distinguish between left and right, any such scheme that you come up with would really fail somewhere or the other. The Ozma problem would have absolutely no solution. It would be impossible to teach an alien what is left and what is right, unless, as long as the laws of physics were the same for left-handed or right-handed coordinate systems, or was the same under mirror reflection. But before we go there, before we go on to the next part and talk about whether Ozma problem can at all be solved, first let's take a look at some more familiar applications of symmetry. The next section is going to be a bit more technical, but it also will be about high school physics, or at most first year, second year physics. In fact, all that I'm going to talk about, you've already learned in high school. Okay, so at this stage, we are going to start looking at some familiar applications of symmetry. Again, as physics students, everybody knows these problems. So look at the heading. It says, it is obvious from symmetry that. Okay, the question that we are often asked as in standard physics textbooks, determine the electric field due to a uniformly charged infinite straight wire. Now, this is a problem which all of you know how to solve. You can use Coulomb's law and integration, or you could use Gauss' law, which is what I'm hinting at. So, from anybody in class 12 has studied Gauss' law and these applications. Of course, first year physics, second year physics, you definitely know about this. And the solution, don't worry, I'm not going to work out the whole thing here and bore you with the details of the solution. But the solution starts usually with this statement. It is obvious from symmetry that the electric field is radially outwards. This is the beginning point. After that, you use this and a few more statements which are again quote unquote obvious from symmetry to decide that you will use a Gaussian cylinder here and then calculate the flux of the electric field to the surface of the cylinder and so on, and use Gauss' law and determine the electric field. But what I'm trying to draw your attention to is this. In almost every textbook, in almost every explanation of this, the solution starts, it is obvious from symmetry that the electric field is radially outwards. So, another question. Determine the magnetic field due to an infinite straight current carrying wire. Here, of course, you use Ampere's law to solve for the magnetic field. And the solution starts with, it is obvious from symmetry that the magnetic field is tangential. So let me just point out that these two systems, a straight wire, infinite straight wire carrying charge, and an infinite straight current carrying wire, symmetries. Yet, it is stated almost as if it's obvious. In fact, it is stated that it is obvious in most cases that the electric field in one case and the magnetic field in another behave completely differently, and apparently both are obvious from symmetry. Now, I would definitely argue that if it really had been obvious from symmetry, then they couldn't have been this different. I'm not saying that this does not follow from symmetry. It does. It does follow from symmetry. You can use symmetry arguments to argue that the electric field in the first case is radial and that the magnetic field in the second case is tangential. No arguments there. All I'm saying is, despite what your textbooks say, it is not at all obvious. There's a lot of thought which has to go into this and the other statements that are made when you use symmetry arguments. And understanding what exactly goes on in those arguments is really critical to understanding a lot of physical aspects of the thing. So, before we talk about this, let's talk about a problem which, well, of course, I've already said this. How can both these conclusions be equally obvious? The answer is they can't. They're not obvious. They have to be figured out and thought about carefully. But to illustrate what is at stake here, let us look at a problem which is an old problem to anybody who has studied physics at the honors level, let's say, or at the BSc level. This is a problem which was there in a book, in a very favorite book of mine, Griffith's introduction to electrodynamics. In fact, it used to be the very first problem in the second chapter of the book. The second chapter is where the physics started. The first chapter was essentially mathematical preliminaries. So in a sense, this was the first problem in the book. And the old version of the book had this in a beautiful way. The question was, there are 16 charges plus q at 16 of the corners of a regular 17-sided polygon. So as you can see, I hope this is visible, there are 16 charges here. I don't need you to count, I have counted. There are exactly 16 of these black dots, which are black circles, which are indicating places where charges are. And there's this one empty corner which is there, which is shown by this open circle, the unfilled circle. So there are plus q charges at each one of these corners, and you have to find out the field at the center. And what made this problem a favorite of ours in Griffith's old edition is the hint which came with it. The hint said just this much: if you are taking more than 30 seconds to answer this question, you are doing it wrong. End. That was the hint. Well, I hate it that the modern edition of Griffiths has actually changed the question, has broken it up into steps, given lots of steps and so on, given lots of extra hints, and essentially murdered what used to be a wonderful question. So those of you who are studying now will not get the full fun of it. The fun was in the hint, which was there in the older versions. If you take more than 30 seconds to do this problem, you're doing it wrong. That's it. And that essentially told most of us how to proceed. The answer was simply this: if you filled up that empty corner with this red dot here, and put a charge plus q there as well, if all the vertices of a 17-sided polygon, regular polygon, are filled, then the field at the center must be 0. And therefore, the field of the 16 charges, our original problem, plus the field due to this one charge must be 0, the superposition. The field due to the 16 charges must be opposite to the charge field due to this one charge. So it must be 1 over 4 pi epsilon 0 q by r square, directed towards the empty vertex. The field due to the charge here would have been directed away from it. Since that field plus the field of the 16 gave you 0, the field of the 16 must be just this magnitude directed towards the empty vertex. So that was the problem in Griffiths. And a pretty easy one. I'm pretty sure most of you know how to solve this. But now I have a challenge for you. The challenge is the answer to this question, which is taken to be obvious in this 30-second hint of Griffiths. Why is the field at the center 0 when all the vertices are filled? Well, one answer to this would be simply this: if all the 17 charges are there, all the 17 vertices are filled with charges, you would have 17 electric fields directed towards them, towards each one of them. And you can easily add up these 17 electric fields. It's not as difficult as it sounds. After all, you can use the polygon rule very simply to show that they add up to 0. But can you do this without adding up the vectors? After all, if you're adding up 17 vectors, why don't you add up 16 of them and find out the answer directly? Can you find out this result? Can you prove that the field at the center will vanish without adding up vectors? Indeed, without even using Coulomb's law. You don't need any law for this except symmetry. And the answer goes this way. Without knowing anything else, we would say, okay, that is possible. It's possible that there's an electric field component out of the plane of the mirror, and there's an electric field component in the plane of the mirror. But if I rotate the system by 2 pi by 17 or 360 degree by 17, 1/17th of a full circle, what will happen is all the charges will just move to the next slot. So if you were looking at the system before and after this rotation, you should never be able to tell the difference. So what happens to our electric field vector when you do this? The vertical component, the component pointing straight at you, that's along the axis of rotation, that doesn't change. The component which is in the plane, the blue line, that has changed. Now, if the charges have not moved at all the charges that were there before, of course they have moved, but now again you have exactly the identical charge distribution as before, and the point where you're measuring the field, the center, that has also not moved. The electric field simply cannot change. But as you can see, the electric field before was pointing straight at you, one component, the other component was this way. Here, the vertical component, the component pointing at you, is still there. The in-plane component is turned around. That simply means that this in-plane component must vanish. There cannot be a component of the electric field in the plane. It has to be perpendicular to the plane. Now you must say, now we have the solution. After all, we know that all the individual electric fields, due to all the charges, are in the plane of the polygon. So since we have now argued that it has to be perpendicular, it must be zero. But I would say that that's really not correct as an argument, because arguing that all the electric fields are in the plane essentially presupposes Coulomb's law. Remember, we are not allowed to use that. We can only use symmetry. So the question is, can we think of some other symmetry operation which will also leave all the charges where they are, and the point where I'm trying to measure the field again at the same place? Then, since the point is the same, the charges are the same, the electric field must be the same. Now there are several other symmetries that you can use here. The one that I want to use in particular here is reflection symmetry. Imagine that this plane is a mirror and you're reflecting the entire system in that plane. What would happen? This is what happens before the reflection. The electric field is pointing straight out at you. Let's assume it's pointing straight out at you. And the blue plane here is our mirror. So if I reflect in this mirror, what will happen? All the charges will stay at the same place. That's the right-hand picture here. But the electric field, which was pointing out, must now point in. So electric field normal to the plane must reverse on reflection in the plane. The electric field in the plane could not have reversed, but that's not there. We have already argued that. So now what happens? If there were electric field at all, it would have reversed, but because the charges are the same, the point is the same, the electric field has to stay the same. So it has to stay the same yet reverse. Now that would mean that it has to be zero. It must be zero, because the only thing which can reverse and yet stay the same must be zero. So that is our argument. So no problems. We have managed to prove something which we all knew. The electric field at the center of a regular polygon with charges at every vertex must be zero. So if you want to say this in a slightly more pompous language, it goes this way. Our system has C17 symmetry. C17, 17-fold rotational symmetry. Remember, the angle through which you could rotate was 2 pi by 17. Then twice that, 3 times that, 4 times that. There are 17 separate rotations you could do, each of which would move all the charges to the next vertices. So your system would have C17 symmetry. Under 2 pi by 17 rotation, the system doesn't change. Neither does our field point move. So this is just a recap in the symmetry language from what our pictures told us. The conclusion was electric field must be normal to the plane. It is also symmetric under reflection in the plane, our system, and the normal component must vanish because under reflection the normal component reverses. So if it has to stay the same and yet reverse, it must be zero. So this was our symmetry argument. So this is fine, and it was pretty straightforward. Now let's see can we talk about a ring carrying current and talk about the magnetic field at the center? So the system here actually doesn't have C17 symmetry, it has C infinity symmetry. You can rotate it not only by 2 pi by 17 and its multiples, you can rotate it through any angle about the axis, and the ring will stay exactly the same. The point where you're trying to measure the field stays exactly the same, which essentially means that for all these rotations, nothing changes. So the in-plane component of B, magnetic field, must be 0. Same argument as for the electric field. But now comes the point. Reflection in the plane is also, so this blue line, among the two blue lines, this one I know it must be 0, because if it were non-zero, rotating the system would have changed the magnetic field, but it can't. But reflection in the plane is also a symmetry. So what happens when I reflect? Well, remember, this component is no longer there. All you have is this vertical component, or perpendicular to the plane component. And if you reflect, the perpendicular component should reverse, yet stay the same. So what we have managed to prove is the magnetic field at the center of a current carrying coil must be 0. And we have proven this using symmetry, which is one thing which we should not really be able to argue against. Now, of course, all of you must realize that there is a problem here, because if this were correct, then we would have had no civilization as we know it. If you think about it a bit, the very fact that modern civilization at all exists, good or bad, that it at all exists, is dependent on a very large part on the fact that there is a magnetic field at the center of a current carrying coil. Almost all of our modern technology depends on that in some form or the other. So if symmetry really led to this result, that the magnetic field at the center of a current carrying circular ring is 0, then we would be in deep, deep trouble. Well, we are actually in deep trouble, because we have used a very nice argument due to symmetry, and yet that tells us that there can be no magnetic field at the center of a current carrying ring. The answer to this puzzle is this: the magnetic field is not a vector. Now that's a big thing to say, but just bear with me a while and I will explain what this statement means. Well, to understand this, let us think about what happens when you reflect a vector. Imagine that the green rectangle that you see in front of you is a mirror. It's a transparent kind of mirror, so you can see also behind what's happening behind it. And this is one place where I actually miss being able to do this lecture physically, because whenever I try to explain this thing in a classroom, what I do is I ask my students to imagine that the blackboard is a mirror, and I walk across it and walk in front of it and say, okay, imagine that my walking is being reflected in the mirror, and say, understand what happens. So I will just ask you, this is one thing I cannot do now in this online format. So I will ask you to imagine that this green thing is a mirror and somebody is walking in front of it. If this person, let's say me, we're walking from left to right like this, parallel to the mirror, the image will also walk in the same direction, right? Parallel to the mirror. So if you imagine, well, if you think of this as a velocity vector, the component parallel to the mirror stays unchanged on reflection. The component perpendicular to the mirror, if I were to move away from the mirror if I were to walk away from the blackboard, my image on this blackboard come mirror would move back away from me, right? Component parallel to the mirror stays unchanged, component perpendicular to the mirror reverses. So this is what happens to a vector if you consider both its components. It's easy to think about this in terms of the parallel component staying the same, the perpendicular component reversing. This is how a vector behaves under reflection. So, as was mentioned a while ago, a cross product. So, what happens when we take cross product of two vectors? Let's say we take two vectors. Now, right now, we are considering two vectors, A and B, which are both parallel to the plane of reflection. Of course, their images AR and BR, are the same, right? They stay the same because they're parallel to the plane of reflection. Now, what about A cross B? A cross B, of course, is perpendicular to the plane of the mirror because it's perpendicular to both A and B. That's A cross B. However, what happens to A cross B when you reflect? It becomes AR cross BR. A becomes AR, B becomes BR, and they stay the same. So AR is the same as A, BR is the same as B. So what happens to A cross B? The answer is simple. A cross B stays the same. Notice A cross B is directed away from the plane of the mirror, yet it must stay the same because neither A nor B has changed. So this is the first indication the cross product of two vectors actually is very different from a vector. When you reflect, A and B in this case has stayed the same, so A cross B must stay the same despite being perpendicular to the plane of reflection. Well, think of another situation. A is in the plane, B is perpendicular to the plane. So this is what AR and BR are. AR is the same as A, BR is reverse of B. A cross B, of course, you calculate the cross product, has to be in the plane, right? It has to be perpendicular to both A and B, so it has to be in the plane perpendicular to A, P being perpendicular to the plane. But since BR has reversed and AR has not, AR cross BR must be reversed. So notice that what happens to cross product of two vectors under reflection is exactly opposite to what happens to the vectors. For vectors, components in the plane stay the same, perpendicular to the plane reverses. For cross product of two vectors, components parallel to the plane reverses, as in this example, and components perpendicular to the plane stay the same. Now, why is cross product called a vector? We always called it a vector, right? It's called a vector because if you were to rotate your coordinate system, the cross product of two vectors would behave just like a vector. So the components will change in exactly the same way. That's why we call it a vector, more precisely a vector under rotations. So if your world only involved rotations, and if your only symmetry were rotations, and that was the only thing you were interested in, you would not be able to distinguish between vectors and this new kind of object, the cross product of two vectors. However, on reflection, they behave just the opposite as vectors. Whatever a vector does, a cross product of two vectors does exactly the opposite thing. So they are a new kind of thing, not really a vector. They are called pseudovectors, as many of you know, also known as axial vectors. The term vector in the name simply is a remnant of the fact that they are vectors as far as rotations are concerned, but they are really not vectors when you talk about rotations and reflections. In particular, under reflections, they behave differently. So what is a pseudovector? Well, a pseudovector is something which behaves like our cross product a while ago. What happens when you reflect a pseudovector? Well, the in-plane component reverses just the opposite to what our vector was doing, and the out-of-plane component, the one perpendicular to the mirror, stays the same. This is the behavior of pseudovectors under reflection. Okay, and of course, if you think of both components together, this is how the red vector would reflect into this pseudovector. If this were a pseudovector, not a vector. And the answer to our puzzle there was the magnetic field is a pseudovector, and because it's a pseudovector, the reflection in the plane of the mirror does not reverse it. Remember, we had already argued that the magnetic field has to be perpendicular to the plane of the mirror, the plane of the circular loop. Reflecting in that plane would actually keep it exactly the same. And hence, it does not have to vanish. Remember, the only reason why we argued that it must vanish is that it reversed, yet stayed the same. It does not reverse because it's not a vector. That's the real answer. Okay, now, having said this, let us quickly answer the question that I raised at the beginning of this section, which is, why are two opposite things obvious from symmetry? So this electric field due to a uniform straight wire. So this, imagine that this blue line in the middle of the page is a uniform infinite straight wire. Of course, it's infinite. I've just drawn it as finite. And this black circle is a point in front of the wire somewhere. And the electric field at this point could, in principle, have three components: a radially outward component, which is this line here, a vertical component parallel to the wire, and a cross-radial component, the one along the tangent to a circle which you could draw here. Now let's argue using symmetry alone that the electric field has to be radial. For that, we want to find a symmetry which will keep this wire unchanged, that will also keep this point unchanged. Rotation about this wire is, of course, a symmetry, but that will move this point from this place to another place on the same circle somewhere. That's actually a very important symmetry for this problem, but we are not going to talk about that right now. We are talking about a symmetry which will keep the point unchanged. And there's one very obvious symmetry there, which is just imagine that there is a mirror which contains the wire, and there are infinitely many planes which contain a straight line. So it's just one of those planes, but the one which passes through my point. So it goes through the black circle here. And imagine that I'm reflecting in this green mirror. So what will happen? Electric field, remember, is a vector. So what happens to the electric field? The component in plane will stay the same. So these two components, the radial one and the vertical one, they are both in the plane. The component perpendicular is the cross-radial one. That one is directed normal to this plane. Okay. So when I reflect, the wire, of course, doesn't change. It stays exactly where it is because it's on the plane of reflection. The point is on the plane of reflection, doesn't move. What happens to the electric field? These two components stay the same, whereas the one which is perpendicular to the plane, the cross-radial component, that reverses. Now this means that if I were to look at the system before and after the reflection, I should be able to say that a reflection has occurred because the electric field has changed. But I shouldn't be able to say that. That's what symmetry is all about. I do a transformation, and before and after everything stays the same, the wire is the same, the point is the same. So I should not be able to tell that I have done this reflection. So the component perpendicular to the mirror, in this case the cross-radial component, that must have been 0, because if it were there, then I would not be able to I would be able to tell whether I have reflected, and I should not be able to tell. Well, now I have two components, the radial one and the vertical one. Now imagine another reflection, a reflection in a plane which is perpendicular to the wire, bisecting it cleanly. Remember, this is an infinite wire, so no matter where you place this plane, there will be equal amount above and below. And I've chosen this plane in such a way that it passes through my point. So what happens when I reflect here? Simple, the in-plane component, the radial one, stays unchanged. The outer plane component, the vertical one, reverses. So I must argue again, because I should not be able to tell whether I have reflected or not, the component in the plane, the radial component, must be the one that is non-zero, is the only one that can be non-zero. the vertical component has to be 0. So this is the argument, this is the symmetry based argument which says that the electric field at a point near an infinite straight current carrying wire is radially outwards. Just to illustrate the difference, what happens with a magnetic field and a current carrying wire? So I have a magnetic field due to a current carrying wire here. The current is going from top to bottom. And again, I started with an arbitrary point, and ab initio, all three components, the radial, the vertical, the cross-radial could have been there. I have to argue that two of these components are actually not there. And here the argument, believe it or not, is actually simpler than the previous argument. Just imagine reflecting in this plane. If you reflect in the plane, the current stays in the same, the wire stays the same, the current stays in the same direction. Because all the electrons, which of course are moving down here, are actually moving in the plane. So when you reflect, they're moving in exactly the same direction. The current stays upwards. The point stays the same. But now remember, the critical thing is the magnetic field is a pseudovector. And what does the pseudovector do? Both components of the pseudovector in the plane must reverse, and the component perpendicular to it must stay the same. So this is what happens when you reflect. And now we have got to the answer. Because you should not be able to tell whether you have reflected or not, both the components in the plane must vanish. And so the only component present, of course, my perspective is a bit skewed in this picture. This is really cross-radial. It's perpendicular to the circle that you draw along the tangent to the circle. So that's the obvious from symmetry, that argument. As you can see, it's not obvious at all. It's really reflection symmetry at play here, and the fact that the magnetic field and the electric field behave differently under reflections because one is a vector, the other is a pseudovector. Now this is a critical point, and that's what we are going to use in the next part of the lecture. Of course, once we have established this, the rest of the calculation everybody knows, so I'm not going to worry about that. Now, it's all right to talk about reflection, but we did mention parity at the beginning, also in the middle somewhere. So what has parity got to do with it? Okay, well, parity is actually intricately related to reflection in a way simpler than reflection. Under parity, what happens? Parity is a mathematical operation where a point xyz in your coordinate system gets transformed to the point minus x minus y minus z. So x changes sign, y changes sign, z changes sign. Or you could say, I've just taken all my coordinate axes and flipped them in the opposite direction. So what used to be my positive x-axis is now the negative x-axis, positive y-axis, negative y-axis, and so on. This exactly is what changes a right-handed coordinate system to a left-handed coordinate system, as you can easily check. So what happens to a vector under this? Because all my coordinates have reversed, all the vector components also reverse. So the vector A goes to A under parity, and it becomes minus A. So realize that parity is in a sense simpler. Always a bit more abstract than reflection. Reflection you can see in your daily life. You can see what happens in the front of a mirror. Parity is more abstract. You don't get to see a parity operation done in real life that way. You don't have a special kind of mirror which will take you and move you to the parity reverse position or produce an image in the parity reverse position. However, describing vectors and pseudovectors become much easier using parity, because under reflection you have to worry about what happens to the in-plane component, what happens to the out-of-plane component, and so on. Under parity, there's just a change of sign. AP goes to minus A. So what happens to the cross product of two vectors? If you have two vectors A and B, both of them are vectors. Under parity, they both change sign. And by the magic of maths, that two minuses make a plus, which we have learned from early childhood, C changes to minus A cross minus B, which is A cross B. It doesn't change at all. So vectors change sign under parity, pseudo vectors don't. That's as simple. So under parity, vectors pick up minus signs, pseudo vectors stay the same. Okay, now I'm going to skip some of the details here simply because I'm running out of time. By the way, Nobo, can you tell me how long can I go on?
There is another 12 minutes as per we follow our existing schedule.
Okay, so can I go 5 minutes beyond that, or do I stop at 12?
Sure.
Sure what? Sure to which one?
Sure to go beyond 5 minutes.
Okay.
5 to 10 minutes.
Try not to go very much beyond, but then I will cut down a lot of the rest of the lecture. But anyway, that's fine.
Okay.
So I'm just cutting down this part. This is technical, but it just shows that reflections are related to parity and rotations. And now let's answer the question. And somebody mentioned the Lorentz force law. So let's answer the question as to why is magnetic field a pseudo vector? The answer is this Lorentz force law is a law of physics. And if we assume that the world in the mirror, which is same as the parity reverse world, is the same, has the same laws as our world, Lorentz force law should be equally valid there. But what happens to Lorentz force law when we do parity? Now you know that under parity, Q stays Q. That's a scalar, it doesn't change. That's charge. What happens to the force? Force is a vector, of course. Position is a vector. That's really the starting point. Velocity, which is the derivative of position with respect to a scalar, the time, is a vector. Acceleration is a vector. Mass is a vector. So force is a vector. So it picks up a minus sign. Velocity also picks up a minus sign. So these are the things which you already know. Charge is a scalar, F is a vector, V is a vector, so they will become minus signs. So what will happen to the equation? If you want the equation to stay the same, F is changing sign, right? Q is not. So if you want the equation to stay the same, E must change sign, but B must not, because here the change of sign is already there through V. So only if you have E a vector and B a pseudo vector will the Lorentz force law stay a valid law of physics under reflections. So now there's a quick thing that I might add to intrigue some of you. All this depends on the assumption in a way that we made that Q is a scalar. Well, does anybody know what a charge looks like when you look at it in the mirror? Is it a positive charge or a negative charge? I'm pretty sure many of you will find this crazy, but let me put this to you. If you assume Q is a pseudo-scalar, something which changes sign when you reflect, even then the laws of electromagnetism will stay the same in the mirror world, but then E will have to be a vector and B will have to be a pseudo-vector. Sorry, I just stated what is usually the case. If Q is a scalar, this is what has to happen. If Q is a pseudo-scalar, E will have to be a pseudo-vector and B will have to be a vector. And that sounds absurd, and especially given the fact that we know which way an electric field points away from a wire and so on, you might say that we can easily show that that's not true because electric field is really radial. So we already used E is a vector for that. But I will ask you to think about it. If Q were a pseudo-scalar and E were a pseudo-vector, B were a vector, you would get exactly the same conclusions that we have reached a while ago. E would still be radially outwards, B would still be cross-radial. This is an exercise, just think about it. So the fact that Q is a scalar is more a convention than something which is sacrosanct or physics driven, but it's the obvious convention to make. Why complicate things? Q is a scalar, works wonderfully well. So the assumption that we had made here, we had actually made one big assumption in the previous slide, is we had assumed above that the laws of electromagnetism are the same in the actual world and the mirror world. So in the original and reflected frames or original and parity changed frames, they were the same. That's why we said, since F is becoming minus F, the right hand side also must pick up an overall minus sign. The prior to the 1960s, 1957 to be precise actually, scientists had assumed that this holds for all of physics, not just electromagnetism, that the laws of physics are the same in the original frame and the reverse frame, actually held for all of physics. That was the assumption before 1957. And if that really were the case, then of course the Ozma problem that we started with would have no solution whatsoever. There will be no way you can convince an alien or communicate to an alien what is left or right without sending him or it an asymmetrical object. This changed in 1957 with the declaration of the results of Madame Wu's experiment. And today, we know that at least there's one corner of physics, the corner that deals with weak interactions, which actually strongly violates this symmetry under parity. So, okay, given that I have only 10 minutes, I will quickly go through this. In the early 1950s, two elementary particles started troubling physicists a lot. They were called the tau and the theta, and they could decay in different ways. Tau plus minus decayed in two different ways. 3 pions, the details are unimportant. Another, the theta, decayed into 2 pions. Okay. So fine, two different particles decaying in different manner, not a problem at all. However, the two particles, the tau and the theta, try to measure their mass, their spin, their lifetime, they turned out to be nearly identical. As far as people could tell from the experiments that they could do at that time, they were identical particles in all respects. So that was a puzzle. How could two different particles behave exactly identical in all other respects apart from decay? So this was a big puzzle. Of course, one solution could have been they're not two different particles at all. They're the same particle. After all, as you can see here, tau itself decays in two different ways.
Hello,
so why couldn't we say that it's one particle which is decaying? Is there a question? Hello?
Sir, your presentation is done. Presentation has done. I mean, your presentation is not showing on the screen.
Oh, I'm seeing a resume presentation. Has this been the case for a long time or now?
No, not that. You have to.
Just a few seconds before.
অন্য পয়েন্টে বোধহয় পিন করতে হবে অন্য জায়গায় তো একজন কোনো এই সময়
No, my presentation stopped actually. Somebody else might have presented in between.
হ্যাঁ সেটা কিন্তু ওটা আমি বলছি আমি অন্য স্ক্রিনে পিন করতে ওটা এসে গেল
আচ্ছা
It's okay.
Okay, anyway, is it back?
Yes.
Okay, so the question was, why are we so sure that there are two particles? There could be the same particle decaying in 3 different ways. After all, tau could decay in 2 ways. Why not decay in 3? And the answer to that, would require us to understand something called parity conservation, which would bring us a bit into quantum mechanics, and that would be what I would talk about in the next 2 slides. But let me just quickly skip this. This is just the only bit of non-trivial maths that we had. The basic idea was there is something in quantum mechanics which is not there in classical mechanics. Parity has a different manifestation. It's called the parity eigenvalue, or just called parity usually. It simply says that you may have states which stay the same under parity, or even functions. That is, if you change x to minus x, y to minus y, z to minus z, it doesn't change. Or you could have odd functions, they change sign. And this parity, if your system has a parity symmetry, this quantity must be conserved. And in 1953, Dallas showed, and this is a very involved, complicated argument. It's not as simple as I'm trying to make it out here. Well, it's not very complicated, but still requires some amount of detailed argument to get here. But roughly, he showed something like this. Pions essentially carry a parity of -1. So 3 pions give you 3 minus 1. So it has an overall parity of -1. And 2 pion states, 2 minus 1 gives you +1. So now the question is, if parity really were a symmetry, which everybody believed at that point of time it was, then parity should be conserved. The tau and the theta must be different particles because they had 2 different parities. So as long as parity is conserved, tau and theta had to be 2 different particles, and so you had this puzzle. 2 different particles, because one decayed into 3 pions, the other one decayed into 2. So one had to have, tau had to have parity -1, theta had to have parity +1, but identical in all other respects. So then comes the question, is parity conservation really sacrosanct? And this doubt was actually raised in private by the experimentalist Martin Bloch to his roommate in a conference, Richard Feynman. So Bloch said, okay, everybody is saying if parity is conserved, parity has to be conserved, so these 2 particles are different. What if parity is not conserved? And Feynman, Bloch himself did not raise this question in public, but Feynman raised it for Bloch. So there was this international conference on high energy physics at the University of Rochester in April 1956. The dates are important in the sense that you should realize that this whole story actually takes place over a very, very short period of time. In April 1956, Richard Feynman asked this question. He mentions Martin Bloch. He says, Martin Bloch has asked me to ask this question to you. Who does he ask this question to? He asked this question to C.N. Yang, who had actually just finished presenting a proposal by T.D. Lee and himself. They had this idea which was crazy and nobody really liked that idea at that time, that there is something called parity doubling. That is, the same particle may sometimes exist in parity 1, sometimes exist in parity -1 states. That went against what most people knew about particle physics at that time. But since this was a disparate problem, Yang and Lee had come up with this parity doubling idea. And at the end of their presentation, Feynman rose up and said, okay, fine, you are saying that parity doubling will solve this. But that actually says, means that you must accept parity as a conserved quantity. That is why you are saying the same particle stays in -1 for some time and then decays into 3 pions, +1 for some other time, then decays into 2. What parity is not conserved at all? What if the same particle, whatever parity, can go into -1 and +1 both? By the way, Feynman himself did not really believe this. He raised this question. He had actually taken a bet with another friend, a $50 bet, saying that parity will be conserved, so this proposal must be wrong. But still, he was under obligation to raise this question. And Yang and Lee had no immediate answer. They just said that we don't know, we have to check. By the way, Wigner, who was also in this meeting, Eugene Wigner is the grandfather of symmetry arguments in quantum mechanics, who actually was behind all these ideas of parity conservation, etc. originally, was the one person in this conference who said, okay, this might have merit, that this idea of parity non-conservation may be correct. But Yang and Lee did something nice. They did not have an answer, but they decided to look further. And they decided to take a very careful look at what was the experimental status for parity conservation. Theory may be wonderful, symmetry and everything is great. However, what is important is, does experiment really verify parity conservation? And the conclusion that they reached was this. In strong interaction, electromagnetism, they didn't even bother about. It was already well known, all the equations were known, they were known to be parity symmetric. In strong interactions and weak interactions, these were the 2 things they were really talking about, nuclear interactions. In strong interactions, there were indeed many experiments that established parity conservation to a high degree of accuracy. So, strong interactions, parity conservation, no problem. Past experiments on the weak interaction have actually no bearing on the question of parity conservation. So what they found out that all the experiments that had been done so far, this was 1956 of course, on the weak interactions, which causes beta decay, as many of you know, among other things, these interactions had no bearing on the question of parity conservation. So these experiments really did not check whether parity is conserved or not. So the answer was this: for strong interactions, we know parity is conserved. For weak interactions, we simply don't know either way. So Young later said in his Nobel lecture, the fact that parity conservation in the weak experiments was believed for so long without experimental support was very startling. But what was more startling was the prospect that a space-time symmetry law, which the physicists have learned so well, may be violated. This prospect did not appeal to us. So while they were saying, we have not checked, physicists have not checked parity conservation for weak interactions, they were really, at the back of their minds, they were sure parity would be conserved for weak interactions as well. But being good physicists, they actually answered the question. They published, in October 1, 1956, they published this paper, Question of Parity Conservation in Weak Interactions, where they raised this question. Okay, this, as I said, physics community more or less was lukewarm to this. And later on, a year later, Feynman Dyson said they were being stupid. Physics community as a whole, they did not pay attention to this question, which was really a great question to ask. But what Lee and Young, this is a picture of Young on the left and Lee on the right. They were rather young at that time. In their 30s, I guess. They said that, okay, not only are we specifying theoretical reasons for believing that parity may or may not be conserved, they are going to state exactly what kind of experiments you need to do in order to be able to judge whether parity is conserved. So to decide univocally whether parity is conserved in weak interactions, one must perform an experiment to determine whether weak interactions differentiate light from left. So the first time we were talking about an interaction differentiating between left hand and the right hand. And the conceptually simplest idea that they gave was this. In their paper, they talked about this. Look at the beta decay of cobalt-60. We know cobalt-60 is a spinning nucleus. It has a nuclear spin. It's an angular momentum. And we know that beta particles come out from it, on the decay. Now, if you look at this in the mirror, let's say you're looking at this mirror this way. Of course, in this mirror, the spinning particles, spinning cobalt-60 will spin the other way. Okay? But the electrons will still be going in the same direction. Right? So this is the original cobalt-60 nucleus spinning and decaying, emitting not one cobalt-60 nucleus, but many cobalt-60 nuclei emitting beta particles. I've just shown one of them in this picture. In our world, let's say you have more particles going down, more electrons going down than up. Then in the mirror reverse world, also you will have more particles going down than up. But notice that in the mirror reverse world, the spin of the cobalt nucleus has reversed. So if all the cobalt nuclei were pointing in the same direction, if I should not be able to differentiate between the mirror reverse world and our world, I should be able to say that as many beta particles should be decay, produced by the decay should be going in the direction of the spin of the nucleus as in the opposite direction. If there were a slight asymmetry there, if more were going in the direction of the spin than in the opposite direction, then the opposite would have happened in the mirror world. So this was what Lee and Young told us, that if you were to look at cobalt-60 nuclei, all of them spinning in a given direction, and look at the decay, if parity is conserved, you must have as many beta particles coming out in the direction of the spin as in the opposite direction. Any asymmetry there would be a sign of parity violation. So before submitting the paper, Lee had discussed the experiment with C.S. Wu, another Chinese expatriate who was working in the same laboratory, same institute as them. And Wu was on the verge of going out on a family trip to Europe and the Far East, but she immediately realized that this is a very important physical problem, and she also realized that it was well within her capabilities, with some help, to solve this. So she cancelled the trip, but she also knew that she could not do this alone, so she tied up with the cryogenics physics laboratory at National Bureau of Standards, NBS, Washington. Because one thing, you need to align all the cobalt-60 nuclei in the same direction using very strong magnetic fields, because these nuclei are like tiny magnets. So if you put a very strong magnetic field, they will all align in the same direction. But of course, what prevents them from aligning is temperature. If you have thermal agitation, they will just randomize. So you need to go to very, very low temperatures for this to be done. Today, this is a sort of routine experiment in many modern labs. In Wu's time, in 1956, this was a very, very complicated thing to do, cutting near the edges of the technology available. And the team ultimately came up with an experimental setup. And of course, the real challenge was reaching the low temperatures, also maintaining the vacuum necessary so that the gas molecules will not knock the cobalt-60 nuclei helter-skelter and so on. Ultimately, on 27th of December 1956, the group met with the first success, and they found that all the beta particles were emitted in the direction opposite to the spin. Remember, parity conservation would have said equal numbers in both directions. Any asymmetry there would have been violation. But here we see maximal violation. All the beta particles come out opposite to the spin. So not only is parity violated here, parity is violated maximally. And there's a picture of Wu's notebook, which record from December 27, 1956, which records the findings there. This is one of the iconic pictures in the history of physics. The day a cherished law of physics was shown to be wrong experimentally, and this is where the beauty of physics lies. Once experiments tell you your wonderful theory is wrong, you have to change your theory. So ultimately, experiment is the ultimate thing. Theory, no matter how beautiful your theory is, doesn't matter. Okay, quickly, Lee and Wu were not the only group. There were other people doing this work. Leon Lederman, same institute, used a cyclotron and particle decay from a cyclotron. Same month, they published a paper. This was February 1957. So from April 1956, when this issue was raised, to experimental verification, February 1957, very, very short time. Another two people from the University of Chicago, in an entirely different way, established this, again using methods that were proposed by Lee and Young in their paper, but a different method. Lee and Young had proposed several different methods, and 3 of those methods had been shown to actually work. So parity had finally overthrown. So once the experimental evidence for the violation of parity symmetry in weak interactions became unsurmountable, physicists had to come to terms with the new world order. And I will quote Isidore Rabai here. He said, a rather complete theoretical structure has been shattered at the base, and we are not sure how the pieces will be put together. But the important thing in science is, if your theory fails, theory works, that's good news. But if it fails, it's better news, because now you have to look for better theories. Lee and Young received the 1957 Nobel Prize 1 year from their paper for this work. And just to round this off, Ernst Mach had actually warned rather presciently that even instinctive knowledge of so great a logical force as the principle of symmetry may lead us astray. The instinctive is just as valuable as the distinctly conscious. So whatever you think to be instinctively obvious may not be obvious. They have to stand up to experiments. So This is the ultimate lesson of science, that if your experiment, you have to be guided by experiments at all stages. Okay, so what about the tau theta puzzle? Turns out that they are the same particle. Parity is not conserved. They are what we call K plus and K minus today. And a side effect of parity violation is a solution to the Ozma problem. I don't have time now to detail this to you, but I'm pretty sure you should be able to figure out how to use parity violation, especially Wu's experiment, to say which one is left, which one is right. Or rather, to decide which one is the north pole, which one is the south pole of a magnet. And once you do that, EM theory can tell you what is left, what is right. There is a sidelight to this, which is there is a slight catch, and the catch goes this way. We don't know whether the alien is made of particles, matter, right? The alien could have been made of antimatter. And the antimatter, cobalt 60, would behave oppositely to matter cobalt 60. So I would again get into a trouble that way. If our alien were antimatter, they would not know they were antimatter. They would know they are matter. And unless I can send something around from our world, they will not be able to know that they are opposite to us. So then again, the problem would become a problem. But it so happens that something else, a CP symmetry, charge conjugation parity symmetry, is also violated by nature, again by weak interactions. And again, it was a K Mason which told, in this case, the neutral K Mason, K0 Mason, which told us that that's the case. So the final answer is, even if the particle, even if the alien were made of antimatter, we should be able to tell. So I'm not going to go into the details of all this now because I'm out of time. But let me just leave you with these books you can read. The first one anybody can read. This is a popular science book. The New Ambidextrous Universe is a later addition to the Ambidextrous Universe which Martin Gardner wrote. It's a wonderful book which is accessible to anybody with any background. The next two books are actually for physics graduates. You have to learn a bit of physics before you can actually read those books. But they have details of all this that I've been talking about. So I will stop here. And if anybody still has any energy left, I will answer a few questions.